Welcome! Today I'm going to do a video on data analysis in Year 11, Year 12 Physics. Now, the example I've got is actually out of the Year 12 textbook, but it doesn't actually really matter except for the last question, which we'll come to at the end. This could be based off something that's familiar or unfamiliar. Now, this is semi-familiar for the Year 12 because it's about projectile motion. So, just reading from here, an investigation was conducted to determine the effect of launch angle on the horizontal range of the projectile. Now, the idea, simply put, I just get my little pen out. Yep. Find where you're going. Where are you going? There you are. Okay. So just do a little drawing here. Okay, so I launch something at some sort of angle. There's the ground, and it goes a little parabolic arc. And okay, how far that goes is that's your range. So that's your SH. And whatever you launch at, that's your launch angle now. Okay, that's what we're talking about here. All right, so that actually follows, if you ignore air resistance, that actually follows a bit of a formula here. The range, the displacement horizontal, is equal to the initial velocity squared times by sine 2 theta, where theta is the launch angle, divided by acceleration of gravity. Okay, now I've actually written this up here, and I've broken it up. And if you've been in my class, you've seen that I tend to break these equations up into this sort of format. So I focus on, okay, here is the range. All right, that's our dependent variable. That's what we're measuring in this experiment. We're going to graph it on the y-axis. I've actually already done this. Okay, over here on the right-hand side, so you've got your equals. On your right-hand side, you have your independent variable. Now, that is the sine acting on 2 theta. We decided to make this the independent variable, not the angle, because if I graph something that takes a form of variable equals constants times variable, then you get a nice straight line, as we can see here. That's why we graphed sine 2 theta and not theta. Okay. So get rid of my little drawing because I'm going to need some more workspace here in a minute. Okay, so we've given some data. The data actually, the raw data is the launch angle, and what you actually measure is actually the range. Now, we manipulate, in this case, the independent variable so we can graph something more linear. So we have to process, and the first question asks us, complete the table by calculating the missing value for sine 2 theta. If you're not sure, all I did was stick into the calculator. So I just went 40, all right, times by 2, and then take the sine of that, and there you go. So that's the value. So I rounded off the 3 recent figures, sticking with the pattern that we see here. Okay, so I can put you away for now. All right, so draw a graph range on the vertical axis and sine 2 theta on the horizontal axis. Now, I've actually gone and done this because actually it's a bit time consuming. This is the sort of graph paper. In my test, you'll be expected to do this by hand. In your assignments, you can do it on Excel or Google Sheets or whatever you want to wish to use. But you do need to know how to graph things by hand effectively, accurately, as best you can. I've got some special graph paper here in this particular case. And also how to determine things like the slope and whatnot, which we'll come to in a minute. All right, so we've done that. Include a line of best fit. I've done that too. So I give myself 4 out of 4 because I've plotted all the points accurately. I've got axis labels, nice increasing, steadily increasing, nice round numbers. Units were relevant. So this displacement was in meters. Sine 2 theta has no unit. The sines of angles are unitless. If you didn't know, you can actually go and check in this formula, the idea of meters. That'll be meters squared per second squared divided by meters per second squared. If they cancel all that out, that becomes meters, and it's meters, and then times by no unit. All right, the units balance out in here, is what I'm trying to say. Okay, so C, use your graph to determine the horizontal range when the launch angle is 25 degrees. Now I want to find the range, so I want to use this, the y-axis, and I want to find where on the y-axis will I find the angle of 25. Now, I don't have the angles here. I have the sine 2 of the angle. So let's go work out what that is. All right, so I'm going to put a few notes here. Okay, so if I got, let's get a bit thicker. Let's write a bit thicker. All right. All right, so I've got an angle. So I'm going to work out the sine. Oops. I don't know how to use this right. Okay, come on over here. There we go. All right, so we've got sine. So this is for question C. Sine 2 25. All right. Now I've just got my little dinky calculator here. No, scientific is the best I can do. Okay. So 25 times 2 equals 50, and the sine of that 7.66. All right. Sorry, I should say 0.766. What am I saying? Okay, now where are you? There you are. Come here. Okay. Stop it. There we go. All right. So let's go find where that is. I'm going to zoom in for the moment. Zoom into my graph. Now, obviously, you're going to draw your graph nice and big anyway on real paper, which is actually going to be a lot faster than what it took me to do this. But let's find 0.766. All right, so 0.7 would be right in the middle of 0.6 and 0.8. Now, in this particular case, every little square across, since that's like there's 10 little squares between 0.6 and 0.7, so every little square is 0.001. So I can just count another a 6.5 essentially, which would take me there. That'll be this line running up here is 0.75, and the next one's 7.6, and 7.66 would be the gap right in between. So that line there, and the gap between those two is there. So I'm just going to just run this up. So you can use a ruler to do this. Obviously, you should have a ruler because you drew a nice line of best fit. Okay, so right about there. Okay, now what we can do is we can just go across here. All right, looking across. So we're kind of in between these two lines. Now I also have a scale for what's going on my y-axis. So every minor line is 0.025. I've actually gone down one bit. So that's 0.2. All right, maybe I'll just go, I'll call it even. Let's say 0. Sorry. All right. 2 minus 0.025. That brings me down to the next line down there. And then I'm going to minus half of that. So actually, no, I'll just times that by 1.5. Because basically 1.5 lots of these down. So I'm going to times that by 1.5. That should work out okay. Yeah. So round off there. It's about 1.96. That's what I'm going to say. Range. Okay. Okay, range is 1.96 meters. All right, now how does that fit in? Let's have a look. It kind of fits in. It interpolates into here pretty nicely. It fits in, and that's the strategy how you can find other values. Interpolation is when you pick a value that's inside the data set and you go try to find out. Okay, you might pick something on the y-axis and go to the x-axis, or vice versa. It doesn't matter. It's just be careful of unit conversion. So if we've done something, if we messed around with the x-axis, which we have, and you start with degrees, you have to put that through the function. work out what the x-axis value actually is, and then find the y in this case. Okay, so that was part C. Now part D is something that students often get wrong. So let's talk about that. Okay, what people get wrong with part D is they often, so we're trying to find the slope of the line of best fit. Okay, now we're actually going to find the slope of the line of best fit, not the slope from the data. So sometimes people just go, and because this is actually quite nice, because it actually does go through 0, 0, or comes close to it anyway. Some people might just get lazy and just pick the last data point and just do a 2.55 divided by 1. That will get you the answer you want. But, okay, I would probably not give that full marks. I want you to find coordinate points on the line of best fit itself, not the data points. You see, the data points actually, you can see they fluctuate a little bit. I can actually use one of the points I just used. That's what I could go and use. Why not? Because I wouldn't have found it. So let's just go through data points. Okay, so one data point is, I went to the trouble of finding this, so I might as well use it again. 0.766, and that goes with 1.96. Now, you're welcome to, on your line of best fit, pick a nice, easy value. Find. Okay, so for example, why don't I just go and pick this one, because it's on a line, that one right there. So on the graph, you can see, okay, I'm on this major line. I'm not sure what it is. I'll look in a minute. But I'm only one grid line up above 1.0. So that'll be 1.025. Or 1.03 effectively rounded through some figures. So I might just write that down here. 1.03. Okay. Let's find out what the other point was. Okay, come down there, exactly 0.4. Okay. All right. So, okay. So, all right, we've got a good pair of coordinate points. So that's as you go and work out the slope. The slope is your rise of your run. All right, so let's go work that out. Okay, so I don't need to necessarily be that zoomed out. So let's go, let's put this underneath. Where are you? There you are. Okay, let's go find slope. All right, so we'd have 1 point in there. Okay, to let go of the button to do a dot. It's annoying. Now I have to press the button again to actually draw something. Okay. So 1.96 minus, so this is the rise. 1 point. Okay, over 0.766 minus 0.400. Okay. So what's that? That's about 0.93 over 0.366. Okay, let's go calculate, see what that says. Yeah, 2.541. So yeah, it's oh well, why can't you just use the other point? Well, it's bad habits, and If you don't show you're working out that you're picking points on your line of best fit, you will lose marks. That's the key thing we all want to do as best we can. But imagine if the data was fluctuating a lot more than it is now. Picking a data point is generally unsuitable because your line of best fit is meant to be there to kind of average out the fluctuations. But after you've done this well enough, because I can pick 2 points, look, I was off by 1 digit. It's approximately, yeah, that's good enough. Determine the units. Okay, so what's the units? Well, the units is, now you can get it from the formula, but that's actually rather complicated because you actually have to go and cancel down all these units. Okay, the units is the rise of the run. So what's the rise? The rise is in meters and the run is unitless. So basically, okay, you've got, so units, let's write this here, units. Stop it. I'm not going to dot my I's anymore. It's too hard. Units, okay, so you got meters over nothing. Not zero, but no units. More particularly, I'd say unitless. Okay, so the idea that this is actually the unit for this one would thereby, if you have meters over no unit, the unit is meters. Okay, so 2.54 meters. But if it was something else, if it was, yeah, well, we got it from the graph. So is it like, say, for example, I don't know, it could be your prac where it was, what was that one? I'm thinking of your recent year 11 prac. You were graphing time in seconds on your y-axis. No, sorry, time squared, and you had 1 over m. So that would actually be seconds squared over kilograms. That was a tricky one. Okay, but this one's actually a very simple one. Okay, so that's D. Get out of here. Okay, zoom out. Let's see. Okay, I'm having trouble actually reading that. I think I zoomed out too much. Okay, that's actually where I had it. That was what I started. Okay, so you might even zoom in a bit, so you might be able to see this a bit better. Okay, so the equation of the line of best fit. All right, well, that's simple enough. So in this case, now I could probably just write it in here. You there? There you are. Okay. SH equals, if I use their value, I'll use mine. I'm going to use mine. 2.54 sine 2 theta. Because it passes through 0, 0, so thereby it's y-axis equals slope times x-axis, which is what we got here. All right, acceleration due to gravity is 9.8 meters per second squared. Okay, use the gradient of the line of best fit and the formula on the previous page to determine the initial velocity. Now, this is where you match up your slope that you've calculated with this. And this is why I broke this up to begin with. Okay, so we're now up to this question F. Okay, I'll put a little spot there. Okay, so question F. So from the formula, we've got V naught squared over G are the constants that make up the slope. Now, that is equal to, again, I'm just going to use my slope. So there was a show that, so show that it's approximately this. You can use follow on, so if you get this, then you can use it. If you get something way off, then you've probably done something wrong or just not very accurate. If you get 2.1 or 2.9, you probably did a pretty sloppy graph. Okay, if you get something completely wrong, like way off, then you've done something wrong. Okay, so we're going to work out V naught. So I'm just going to rearrange that. Okay, now we know that, okay, let's just move find where you are. Move you across here. All right, V naught squared equals 2.54 times G. Okay. Yeah. Well, it doesn't like drawing. Don't like drawing circles. Okay, 2.54. Yeah, G is not. Oh, I'll just substitute it in 2 point. I have to do it in places. Sometimes it lets me draw in decimal places, sometimes it doesn't. Okay, so 2.54 times by 9.8. Okay, so all right. All right, 24.89. Just for sake of it, I'll write it all out. It's not that much to write. 892, was it? Yeah, and then I'm going to take the square root of that. So square root of that, V naught, I'll round off my last answer. Yeah, stop it. Squiggle, squiggle. All right. Okay, square root of that, 4.99. Let's round that up. Yeah, if I use 2.55, it might have actually been this straight up 5 meters per second, but I got different answers. Oops, forget the square. Why did I write the square in there? Square's got to go. Square has got to go. All right. Sorry. That's the whole reason I took the square root, so the square's now gone. That's better. Okay, so that's your answer for F. The question G, I mentioned that this is actually related to. I'm not going to. I'll answer this question, but it's related to understanding of the content of projectile motion. Now, there's a symmetry between launch angle. I suppose we could do the question. Set another launch angle that give a range of 2.21 meters. Now, you can actually do it from here. For those who've done projectile motion, you might be aware there's a symmetry. If you've got two angles that add up to 90 degrees, ignoring air resistance, they should have the same range if it's unilevel. All right, so then the other case, if that's 30 gets you 2.21, the other angle would be 60 degrees. And if you actually do sine 2 theta of 60, so it'd be sine of 120, you would also get 0.866, which just so happens to be the square root of 3 divided by 2. All right, just a bit of insider knowledge. So I'm actually not going to do G. I'm going to do my own G. My own G is going to be this. Okay, so my question would be, all right, G. All right. Graph a line if this was done on the surface of the moon. Okay, so that's, I'll give it a little hint. G on the moon. Is approximately 1/6 of G on Earth. Okay, so what would happen? Okay, let's leave it there. All right, so now go back to our equation. So what if I was to do this? So I'm changing G. So I'm changing something in the slope. So I'm keeping my initial speed. I can still launch at all these different angles. Okay, what would happen? Well, okay, so G has been reduced by 1/6. So you can just you could divide that by 6. Okay, but what does that happen? You're dividing something that's on the bottom by 6. It's a bit like, okay, if you divide a fraction, you times by its reciprocal. So just be careful with that. What actually the effect would have, would you actually end up with 6 times the 6 times the slope. Now, so you'd actually end up, yes, it would have a multiplier effect of 6. The range would multiply by 6 for the same sine 2 theta. Okay, so what would that look like? Let's use a different color. All right, so let's do some maroon. All right, so if I did 6, so 2.55, if I'm at 1, well, I'll be well above that. I would just make another little prediction here. So if I was to do 15 degrees would be sine 30. Okay, sine 2 times 15. You pull out my calculator. All right. Which I think even that would be too high. Because that'll be 6 times higher than there, and that's off the scale. Well, let's just go with 10 degrees. Okay, what's sine of 10? So I'm just going to rough scale. It's not particularly important like how accurate I get this. If we just get the shape of it right, that'll be fine. So sine of 10. Okay, sine of 10, 1 point. No, sorry, sine. Yeah. Well, that's 5 degrees anyway, and that's about here. Well, actually, I want to compare it to what I had before. Never mind. So I'm going to do sine of 20. So put 20 in. Sine at 20, because that's 10 degrees. So that's here. All right, and at that point, so that's here, which is actually that dot there. So that's, I want 6. No, it's going to be too much. No, let's go with, oh, look, it doesn't really matter. I can just do it from here. Okay, so if I want to do 6 times something, I'll pick a value here. If I do 6 times there, for example, that'll be close to 3, which would be actually kind of up here. Okay, maybe I'll pick something. If I go right there, so that's about 2.5. Now, if I go up, that would be 3 there. So I actually can draw the line. I'll just do it this way. This is a lot easier, just doing it off the graph itself. That's about where it crosses this line here. So that's 0.25. If I go up a bit, if I times that by 6, I'll be up at 3. So basically, I can just take that point up here and draw back. And there, I've got, that is the, I'll put a little marker and say what it is. That is for the, on the moon. And then we know that is. Okay. So there's other things I could ask in this sort of data analysis, but if you're familiar with these data skills, if you're not too familiar with graphing accurately on graph paper, there's something you should ask for help about. I could get some graph paper at some point and do it. It's just time consuming, so I'm not going to bother with that right now. I did this in advance. But other questions they could ask you about, okay, yeah, if you change this, what else would happen? I've just done one example of that. You could change the speed. You could go from the y-axis and have to go work out an angle. So it says, okay, well, what angle would I have to launch at if I wanted to get exactly 2 meters? So you can go across, find where that is. And then you have to go down, and then you have to actually undo it. So you actually have to find the anti-sign, you have the inverse sign, and then times by half, I believe, and just be careful about which angle you pick. So there's a whole bunch of different things you can ask, but I think you get the general idea. That's how you do a data analysis. Okay, thank you.